volunteers here have heard me ask if we could have anybody willing to step up and do presentations on any number of space-related topics. And tonight's guest, Logan Filar, has been so kind as to volunteer for tonight's presentation. And artificial intelligence is all in the news these days. And it's a very timely presentation on artificial intelligence in astronomy. So, Logan, the floor is yours.
So welcome everybody. My name is Logan Filar. I'm a student at Sebastopol High School. And today I'm going to be talking about artificial intelligence in astronomy. So we're going to go through what is AI and how does it work. We're going to look at some applications, some ideas that we could use it for. And then we're going to look at an example of an AI that I actually made last summer, so we could see what the code actually looks like and how we can actually use it. So first, what is AI? AI is, it stands for artificial intelligence. IBM defines it as leveraging computers and machines to mimic the problem-solving and decision-making capabilities of the human mind. So in other words, you're using computers to mimic your mind in a problem-solving way. And these artificial intelligences, they use two main structures to function. The first one is called machine learning, and the second one is called deep learning. So these two, they have their similarities and they have their differences. Depends on what you want to use the AI for. The machine learning uses what are called learning algorithms, and these are blocks of code that can perform tasks without being explicitly programmed. So basically you can give it some information and it'll do a whole bunch of different things with that information, and you don't necessarily need to explicitly tell it to do one specific thing. Machine learning structures are also very good at recognizing patterns and making predictions. So if you give it a list of data, it can see the patterns in that data and it can guess what will happen in the future. And the other thing about machine learning structures is that they can be what's called supervised or unsupervised. And this means that you can have human intervention or not. So if you give it a bunch of information, you can have it go one step at a time, where you give it the information, it does something with it, you stop it, and then you do something else with it, just one block at a time, or you can just give it all of the information and it'll just run with it. Deep learning structures can also be supervised or unsupervised, but the big difference with deep learning is that these actually mimic the way a human brain works with something called an artificial neural network. So what you do is you create a series of algorithms that can connect in various ways depending on the situation, similar to how neurons in a human brain work. Because of this, we actually call those algorithms in the neural network a neuron. So the other thing I have here is what's called a hidden layer. So basically, in a deep learning structure, you have the input, and then a whole bunch of stuff in the middle, and then the output. The hidden layers are just all the stuff in the middle. We call them hidden layers because in the code, you're not always going to see them. Sometimes they can just appear based on the connections of the neurons, but it's just part of the structure. This is an example of what one of those neural networks looks like in deep learning. So you can see the orange dots on the left. Those are the input layers. Those are the information that you're giving the AI, all the numbers, the images, whatever. The green dots in the middle, those are our hidden layers. Those do the bulk of the work. They're doing all of the computing, the manipulation, the question asking, and then it all comes out to one final output at the end. And you can see just from this diagram, just with straight lines already, how many possible connections there are. But you don't even necessarily need to use straight lines. You can have neurons loop back on themselves. You can have them just in any arrangement. You don't need this set number. You can have as many or as few as you want. You can have a 10 by 10 grid of neurons, 2 by 2, 50 by 50. The possibilities are really endless. So let's break it down into the actual neurons themselves. Let's look at those. So each neuron has an algorithm. Essentially, each algorithm is asking a question. Is this image red? Is it blue? Is this number a 1 or a 2? Each neuron receives an input, it asks that question, and then it gives its output to the next neuron or the next layer. The neurons also have what are called weights and bias. These two, they have slight differences, but they both do essentially the same thing. They both affect how important an individual neuron's output is to the overall output. So if you have like an image that you're inputting into the AI, and you have one heavily weighted neuron and one lower weighted neuron, let's say the heavy weighted neuron says the image is red, but the lower weight neuron says it's orange, the overall output is going to be at least mostly red, if not entirely red, depending on how hard you weight the bias. And then this is just a diagram of an individual neuron. So the X's on the left are the inputs. Those are what you're giving it at the start. Then it does its question, it asks how important is the question, and then it gives its output to the next neurons. Any questions about neurons individually or the structures of neurons so far? Yes?
The example you gave was real simple of just, is it red or is it not red?
Yes.
Are all of the neurons at that low a level, like just a binary decision, or are some of them more complex?
They're usually just binary, but what you can do is you can have the weights set to be more 50-50, and then if you have that feed into another lower weighted neuron, then you can get that mixed answer.
Okay, thanks.
Yeah. So now we're going to look at some applications of artificial intelligence in astronomy. Before I show you the next slide, which has some of my ideas, what are some of your ideas? How could we possibly use AI in astronomy? Yeah.
It's already being used in processing the data for astrophotography.
Yeah.
Some of the best tools available, none of them are free, but the best tools available do have AI in them.
Okay. Yeah.
You probably, I would think you could program to track different astrological events, to be looking for them and then
Yeah.
tracking them.
Any other ideas?
Looking for killer asteroids?
Yep.
Sort out the asteroids between the Starlinks.
All right.
In the birth and structures of galaxies, starting from the most basic information that we have, that's fed into neural networks, to come up with what are the best possibilities in terms, and reject possibilities that don't make as much sense.
Yeah. Yeah, so all those ideas are great, and the best thing about AI in astronomy is if you can think about it, you can probably make it. So these are just a list of some of the ideas that I came up while I made this slideshow, but all of those ideas are amazing as well. So you can use it for detection, finding an object in the night sky, where is it? You can use it for classification, to figure out what something is. To further that, you can use it for theorization. What else is out there? Is there a planet that could sustain life? Is there a particle that we're not seeing, some type of force? You can use it to model extreme situations, such as like the Big Bang or the expansion of the universe. Those things are really hard to conceptualize, but an AI is really good at breaking that down and figuring out what could make that possible. And then tracking, you can just keep a record of changes. various types of waves that are hitting the Earth, brightness in stars, chemical compositions of things, and more. Like I said, the possibilities are endless. So now we're going to go into the code of Maya AI, which is used to find exoplanets. But first I'm going to give you a little bit of background information. So first, what is an exoplanet? An exoplanet is any planet that orbits a star outside our solar system. And we are trying to look for these planets. A lot of people have especially been interested in them lately for the search of extraterrestrial life, aliens, all that kind of stuff. It just fascinates people. So we're trying to find more. So to find an exoplanet, what we use is called the phototransit method. What this is you're using the periodical dim in the brightness of a star to determine if there's an exoplanet orbiting it. So if you imagine like a light bulb and you're passing a pencil in front of it, when the pencil passes in front of it, this light bulb appears dimmer for a brief second, and that's what we're doing. We're trying to find that dimness, and if we know that it's orbiting it if those dims appear at a regular interval, because like the Earth, it travels around the sun at 365 days, after 365 days. So it's a regular interval. And this method can also help determine the size and atmospheric structure of a planet. So not only can we figure out where a planet is, but we can figure out what it's like as well. And this method can also be done on a huge scale. You can use it on several telescopes at the same time that are all looking at different stars, and you can really make it into like a huge search. So to figure out if the dimming is at a regular interval, we use what are called light curves. So what we do is we plot what's called the star flux, or the brightness of the star, over time, and then we take out one period of the graph, which is the section from one dip to the next, and then we use the AI, and it overlaps that period onto the graph several times, and it looks at the overlapping dips. So you can see in the top right graph, those dips match up almost perfectly. That means that that star has something that's causing it to dim at a regular interval, which is likely an exoplanet. On the bottom right graph, you can see that the shapes sort of match up, but the timings don't match up. And that means that the dimming is happening, but it's not at a regular interval. So we could say that it's something is causing it, but it's probably not something that's at a regular orbit. One of the last things before we dive into the code is something called data augmentation. So obviously we know a lot about stars. We can keep track of tons of stars, but we don't know a lot about how many exoplanets there for sure are. We have a couple that we know there for sure are, but we don't know a lot. So what we have to do is we have to use data augmentation to help even out that data set. Basically, what this is doing is it's taking the data of the exoplanets that we already know for sure, and it's duplicating them in a way that the AI can figure out the pattern in. Because if we just have like 5 numbers, it's hard to see a pattern. But if we have 50, that's a lot easier. This helps the AI learn, and it reduces what's called overfitting, which is basically where the AI just memorizes the answers. And to do this, we use 5 helper functions. They have very weird names for some reason. But basically, all they do is help create more data to help find the pattern. Okay, so now we're going to get into the code. This version of Maya AI is what's called a convolutional neural network, which is just one type of neural network. It's just a different specific way to structure it, and I did it this way because this is the version that I've found to be the highest accuracy so far. Okay. So, first we have this top block, these top 4 lines. This is importing all the data. So it's taking our big list of numbers and it's taking it into the AI. Next, we have all of these pink letters on the left, all the way down to here. Those all are just taking tools from around the internet and bringing it into the AI. The reason they're there is because I don't want to have to type out like literally a million lines of code. So they're all there and they're taking sources from around the internet and bringing it all into the same spot. And all of these tools are used to help sort the data, put it into readable formats, various things like that. Next we have these 4 lines here that say df train and df test. These are taking our list of numbers from before that we brought into the AI, and it's making it into a readable format for the AI. These lines that say label -1, in our list of numbers that we brought in, all of the numbers are labeled so that we know if it's an exoplanet or not an exoplanet. It's sort of like we gave the AI its homework and its test, but we gave it its answer sheet too on accident. So this is taking that answer sheet back away. Next we have these 2 blocks of code. Both of them start with this blue DEF. These 2 are defining what are called functions. The first one is making a function that can graph how well our AI is doing. And you'll see that in a sec what that looks like. It's just taking how well it's doing over time and making it into a graph. And then the second function is making it so that we can use the AI again. We're not just scattering all of our numbers all over the place so we can never use it again. We're reorganizing it at the end. And then these are our functions that we saw in the data augmentation, where it's making that synthetic data so that we have more to work with so that we can see the pattern. And then these are all just applying those functions to the data so we can actually get our new data set. And then this is where the actual neural network structure comes in. So you can see that right here is a very important line. It says model equals sequential. So what that means is the AI is just going to go left to right in its order. It's not going to do any fancy looping on itself or anything like that. It's just going to go one neuron to one layer of neurons to the next layer. It's not going to loop back on itself. This input shape, that just tells the AI like a rough estimate of how much information you're actually going to give it. In this case, we have about 3,197 points of data to give it, which is a lot, but it's important to give it a lot so it can really define a pattern. Next, we have this whole block right here. So all of these are what our actual layers of the neural network are. So there's basically 4 different types of layers that we have in here. We have this CONV1D. That stands for convolutional one dimension. And what that does is it's taking the data and it's like segmenting it so that we can break it apart and rearrange it. The second layer is called max pooling one dimension. And what this does is it's taking all those broken parts and it's rearranging them so that similar parts are together. And then we do that again. And then we have this flatten function. And the flatten is making it all back into one straight line, so it's not just blocks. It's all one line of code again. And then we have dense. This dense function is making it back into a readable format for us. And then we're adding all that to the model. And then we're adding a couple tools here so that we can actually keep track of how well the AI is doing. And then one of the last steps, we are training it so that it can actually see the pattern. This batch size means that batch size equals 64. That means we're going to give it 64 of those 3,197 data points at a time. So just little blocks, just a couple at a time. Epochs equals 20. That means that each group of the 64 data points is going to run through the AI 20 times. And then the other important thing here is shuffle equals true. That means that each time that the AI gets the data, it's not going to see it in the same order. And that means that it's going to help, so it's not just memorizing the answers, it's actually understanding how to do it. And then we run it, and we see how well it's doing, and then we analyze how well it did. We see what score it got on its test, what score it got on its homework, all that stuff. You can see, well, it's right at the top here. So we have right here, epoch of 1 of 20. That means this is the first time that all the data ran through it. It got 88.9% on its homework and 97.9% on its test. But the thing is here, the test is higher than the homework at the first time it runs through because it just memorized the answers. So we don't want that to happen. That's why we have to run the data through it multiple times.
And you shuffle it too.
And you shuffle it too, yeah. So by the 20th time here, you can see that it got 99.89% on its homework and 99.75% on its test. And just for a frame of reference, 99.75% out of 3,197 is like 8 wrong. So it's pretty good. And then this is just the graphs that we were defining before, how well it did over time. And then this last part right here, which is the most fun part, is it's taking what the AI thought about all of the data, and we're looking at individual stars. So we could say, like, this first line here, individual label 00, that's saying, I gave you a whole bunch of lists of brightnesses of stars. For the first one, does that one have an exoplanet or not? And this AI says that it does, this one here. For the second one, we're asking it, for the 6th star, does it have an exoplanet? And it says no. The reason that's not quite 0 is similar to how like a calculator works, where you give it like a whole bunch of numbers, and sometimes they just overcomplicate things. Like 2 minus 2, and it'll give you some random number. Like, we all know it's 0. That's basically what this is. Yeah. So that's what the code is. Any questions about the code? Yeah.
What input data are you using? Is that JFI?
Yes. So all of this data is run off of data collected by the Hubble telescope. Yeah.
So what is it? Areas of the sky, and it gives you flux versus time for a whole matrix of stars?
So this, for the actual data set, you have to, you could use another program, but for now you just have to manually keep track of the brightness of the star over a certain period of time. For the Kepler data, I think each star has like 2,500 data points. So it keeps track of it for like every minute for like a month. You don't necessarily need that many to figure out your own data, but the more the better.
So this looks kind of basically like a script, and you download the neurons or the functions from those top lines. Like I see you got the wget.
Yep.
Pulls that off the internet, and then up at the top, Google. So that pulls down each of the little, like down there, these, I guess the functions are further down, aren't they? Something model or whatever, is that one of the function things that are?
Oh, this one?
Yeah, where you put the variables in, they're like cove 1D and such. Is that like a function that's downloaded, or just some of those things, or model.add or whatever, is that like model.compile?
Oh, so yeah, those are all parts of the function. So like this is just like the add, it's just adding that layer to the model. They're just various parts of the functions.
Yeah, it just looks like a fairly short, simple code where it pulls off these more advanced things off of somewhere.
Yeah.
So I'm still trying to understand how AI works. It's like, is it like, is it a different programming language somewhere that has all these little neuron things, and you have to figure out which neuron to use in your software to link them together? So I've done some like Visual Basic, Pascal, Basic back in old days, and we write all these little subroutines and then put the variables in. So I kind of assume it's kind of pulls these routines out like from the internet, and then you tie them all together or something, or?
Yeah, so all of these tools.
I mean, what differentiates normal programming from AI, I guess? Is
So all of these tools are essentially normal programming. The actual AI piece of it comes down here, where you're connecting the layers and you're connecting the algorithms in certain ways, so that they can interlock and work off of each other.
Okay.
How do you validate what you're downloading and ensuring that it's not corrupting your initial program you built?
So all of the data is based off of confirmed exoplanets or non-exoplanets by the Hubble telescope.
Okay.
So they've all been confirmed by NASA.
Oh, so you're looking for something different that shows up than Hubble web data, or Kepler data, or whatever. It has all these planets that they've discovered, so it'll look for new ones or something, and it'll kind of compare with some that are already there to validate the data, or?
So all of the data that's already there, it's just using as a guide to actually look for something. Well, I shouldn't say that. You can use this on the old data to figure out if there was a mistake.
If it works, yeah.
And that is something that happens all the time, that they just overlook it, especially when there's over 3,000 data points. But the biggest thing to find something new is you have to get your own data.
Yeah. Hopefully we'll get something from that telescope for you.
That's the next part. So
you're saying that you developed the AI and you're using the old data and the old findings in order to prove that the AI works.
Yes.
So then you could.
And then you apply it to something
new data.
Yeah.
Fresh, yeah.
How do you track down clerical errors? Is that something that's easy to do? I mean, if you had like instead of -14, you had +14. Is that something that would be easy for you to figure out?
I guess it depends on. It wouldn't be that easy. You'd kind of have to get lucky looking at the right star at the right time, especially when there's so many.
Okay.
So it is very difficult, and that's why the errors happen.
I see.
But that's also why they're checking it constantly with these AIs like this. So yeah. So this AI is trained off of NASA's exoplanet database, and this is why I know it's accurate. And so my dream is that we can build up our own data about various stars using the amazing telescope and photography skills you guys have here, and eventually apply that data to the AI and search for our own yet to be discovered exoplanets, and maybe even get a picture of one. So, yeah. Thank you. Any questions? Yeah.
How did you get interested in doing something like this?
So I was really bored last summer, and we found this class that was online, and it taught you how to basically build an AI, and then I took that and extended it to this.
Wow. So
Yeah.
do you share Elon Musk's perspective that AI is completely out of control and like it's developing faster than the ethics associated with it?
I think people have to be careful about what they use it for. Like I said, the possibilities are endless, and by endless I mean endless. So you just have to be careful about what you use it for.
Like any powerful tool.
Yeah, somewhere I saw.
Yeah.
So what would happen then
Okay.
if you implemented your AI tool onto a new star?
Mhm.
And let's just say that it happens that two planets go by at a similar time, or maybe one's starting and while one's ending. If that scenario happened, what might the data look like, or could you differentiate?
So hopefully the AI will be able to see that there's several dips that are happening sort of close together, but hopefully it'll be able to still see that those dips, even though they're close together, they still happen at regular intervals. Hopefully it'll be able to separate the two. The planets would likely be different sizes, not necessarily the same, but not necessarily different, but maybe different, hopefully, and that would also cause different sizes in the spikes, and you could see like the pattern in the big spikes and the pattern in the little spikes.
I'm really curious on how we might go the next step and generate some data that we could feed through this AI.
Yeah.
I've done just a little bit of this, just enough to be dangerous, and the way I've done it is go to a list of known exoplanets, and then watch that star take the light curve for 4 hours.
Yeah.
And believe me, there's no end to what can go wrong. But that's one star. It takes 4 hours on one star, and it's based on a list of known exoplanets.
Yeah.
What would be the logical next thing that we might be able to do as a small organization?
So probably the best thing to do for a next step would be to look at a star that was not recorded by the Hubble telescope, and try to keep track of that star, ideally as long as possible. Like I said, for the Hubble telescope, they got like 2,000 data points. So I'm not necessarily saying we have to get 2,000, that's insane. But the more the better, and just trying to look at a star that they haven't checked yet, and then running it through the AI a couple times and just seeing if it's yes or no. Okay.
Then we gotta name the planet.
I think the name is Logan.
Alrighty, thank you.